Welcome to a short presentation on how to gather your code coverage from a target like an atmega 328P. For this example, we are using the open source platform Arduino. We will use the IDE codeblocks and we will use the open source tool PuTTY. To begin with, I will show you a short summary. These are the 9 steps we will be using to gather our data and analyze how well we have done our tests regarding code coverage. First, we have to set up an IDE. In this case, we are setting up, as an example, the codeblocks IDE with the AVR GCC of version 3.5 provided by Atmel. The next step would be to implement a serial communication. After we have a reliable serial communication up and running, we will implement the HOTA-Library, so it uses the serial communication to send us the data we need to calculate our code coverage. As a last step in the IDE, we compile and instrument our production code with Testwell CTC and HOTA. After we have planned and designed our tests, we have to run these tests and gather these data. After the step, we can completely leave every other tool behind. We just use Testwell CTC++ to convert our gathered data to reports. How this is done will be shown. If our code coverage is insufficient, we have to do everything again from step 5 or even step 4, depending on if we have to rewrite our production code or if we have to rewrite our tests. If our code coverage is sufficient, we just write our final report and that's it. The codeblocks IDE is quite simple to use. I will show you how to integrate it as a normal IDE. To do this, we will edit our compilers. Normally, you can integrate the AVR compiler quite easily, and how this is done, I will show you now. First, you go into your settings to do settings on your compiler. After you've done that, you select the appropriate compiler, for example, the GNU GCC compiler for AVR. This method could be used for any compiler that is invocated via the command line and is similar to GCC. First, we have to find our toolchain executables. In my case, I just put them into the C AVR GNU toolchain, and here is our binary folder where we can find all the executables. We will not be using any C++ here, so our linker for dynamic libraries will also be AVR GCC and not AVR G++. We do not have a valid debugger here, so we will not use it. We also have no resource compiler, and we just erase the C++ compiler out of the whole thing. To compile for the atmega 328, we probably have to add a new flag. You would just enter all the things here. I already made this flag, so I just show you what I've done here. I have set the compiler flag, the linker flag. I put it into a category, in this case an AVR CPU architecture derivative. Maybe you have to modify the whole things a bit different on your machine. You can also put some defines here, but I think this should rather be project specific. So I will show you on how to do this on your specific target. Okay. So we now have an IDE that is running. What do we need now is a serial communication. We just write a small hello world program and try to testify that our serial communication is up and running. We will use for this the PuTTY serial monitor as well as the AVR-Dude to upload our program and our already prepared IDE codeblocks. So what have we to do? We have at first initialize our serial communication. We have to provide a put character. Our get character is just optional here. We don't need it really. We provide a utility called serial_puts, put string to be specific. And we provide here an array of constant 8-bit integers unsigned. We also have a serial gets, but we don't really need it here. So we have already compiled it, wrote it here. First we have to calculate. If we don't have a baud rate in our defines, we will default to 9600. And we will calculate the baud rate prescaler with fr_CPU baud rate times 16 unsigned long minus 1. After that we have enough data to write into our UBBR register. We have one high and one low, both are 8-bit integers, and we enable our receiver and our transmitter. We also define our number of bits. If you have another target, probably you have to adjust these settings to your specific target. So we also have to do some build options on our project. To make things easy, we do a post-build step with AVR copy. We make an Intel hex. We reserve room in EEPROM. We use our executable to generate our hex file. We go into our compiler settings, we set some defines. I defined the baud rate and the frequency of the CPU. I made the little optimization, stripped all symbols from binary, and yeah, here are atmega 328p. Okay. Yes. So save this. Now we build our project. So what can we see here? First, we call our AVR GCC, we compile our main C, we compile our serial, and we link the whole thing together right here. After that we have an exe file, that is our output, and we are running now our post-build step. That's our AVR copy -0, I hex, etc, etc. Now we configure two tools. One is the AVR-Dude, which is used to upload. We give the parameter, in my case it's port 3. I use the C Arduino programmer config. I chose the atmega 328 part number. I just told the uploader to not be that verbose. And here is what does the magic. We go in Flash, write our Intel hex here. Okay, just to show you. So, as we see, we have flashed the whole thing. Now we use PuTTY, which is configured quite similar, but much more easily. We use our PuTTY file, -serial COM3. We stay at our COM serial port. We start our PuTTY, and we will see, for example, hello world. If we are at this stage, we are almost done for instrument or preparing our instrumentations. Close the whole session. See you on step 3. So the next question is, how do we tell our CTC to use the serial communication? In the host target arrangement, we have several files that override the normal behavior of CTC. Normally, CTC would write into a file system, character by character. Because Arduino does not have any file system, we have to use the serial communications here. Before we implemented our serial interface, we need this interface to implement our targ-send.c. To do as little modification as possible, I changed some definitions. I just told them if no stdlib is defined, do not include the standard library, and if no stdlib is defined, please include serial.h. After that, via another preprocessor directive, I excluded the normal implementation and wrote just my own. The important things here are, first, CTC prepare upload, get character, our write out to the serial, and get a new character, and at the end just put a new line, which is translated internally in the serial interface as get rich return line feed. So far so good. We are done with the targ-send. We have to look into the targ-cust. We also have no standard library here, so we do not include the stdlib. Therefore, we do not have malloc. We have to outcomment this line. This line prevents you from implementing targ-cust so that you do not have malloc. But if you do not use any heap things, please refer here to the readme.txt for further explanations. You could just say, if it gets called, just return null as if there was an error. But normally we do not use heap on target testing in this case, so it does not matter. On the other hand, we have the CTC exit. We just trap it inside an endless loop. Show arrow is not used at all, and that's it. That's all customization in this part. And in the targ data C, we just avoid the CTC at exit functionality because we have no stdlib. Normally we do not need our modifications here. So that's it. In this case, I packaged the whole thing just as a static library in terms of code blocks. so I can add it without problems. And in this case, I write it directly as and in this case, I write it directly right into the CTC home. So we have a file named libhota_atmega 328p UART. That's our implementation for our UART in the CTC case. So to mention it, you also need to specify the define for no STD lab. You normally do this under properties, build targets, build options, compiler settings, defines, and here you see the no STD lib that is used for this library. Now the last question is, how do we now integrate the whole thing to use CTC? First, we will have to open a file directly in the CTC home. That is called ctc.ini. In this case, we open it just right into this editor. So we are looking for a specific thing called gcc/target or target/gcc. We have it here. We copy the whole block. Okay. We can now close this file. We have now this ini file already prepared. I just walk through this whole thing a bit with you. We specify how this whole configuration is called, in this case target/gcc. We can also call it atmega 321p. And because it's in the working directory, this is only specific for this project. We have the command here that is called avr-gcc avr-gcc.exe. If you need, just modify it appropriately for your commands that you're using. You can also use it for other compilers. Maybe you have to rewrite some of the params here, but this is not the focus of this workshop. So we have now also a library. We generated beforehand our libhota atmega 328p UART.a that is generated here. Okay. So after we done all this CTC configuration, we can close again the ini file. We now have to set up a compiler that fakes another compiler. In this case, I just copied the AVR compiler and prefixes it with CTC. In the advanced options of the other settings register, I just prefixed everywhere a CTC where it's appropriate. So it's appropriate except everywhere. It's appropriate everywhere except the generation of resources or Win32 resource, but that's not a matter for the atmega. So I then define this custom variable, that's the CTC prefix, CTC minus I for please use the instrumentation multi-condition. Then I made a build target called CTC that uses exactly this CTC GNU GCC compiler for AVR. The rest of the settings still stays the same, and we don't have to do anything else. We won't need to build these things. This thing, we just need that it is there. We also don't need to make it visible here. It just has to be in the working directory, so CTC finds it when it is invoked for building these whole things. Normally you see here the execution working directory. So this is also the working directory when all of these things get generated. We now make a clean and rebuild. Now we see the CTC get prefixed, everything takes a bit longer. And it asks for our license. As you can now see how the whole thing gets generated, we first start with the prefix CTC, and now everything has been instrumented. Now load it up to our Arduino. It's now running. We now configure our tools again for our putty. We edit it to just start our putty, because we have to do some configuration. So we use the serial again on COM3, but this time we will use the logging functionality. We use the printable output. And we write it as mon.txt, because we monitor it and it's the text file and so on. Now we open the session, it starts, it writes out, it is done. Okay, we want to close the session. Now just to look into it, we open again our file. So we're going to, now we have here our mon.txt. We open it directly, and here we see what exactly comes out. If we wanted, we could also just strip away and so far that's it. As we have done that, we now only have to convert this whole things. Now to convert these things, we just use some of the tools provided by CTC. To take a quick look, we just open a command line. Of our project called Hello AVR. Now inside this we have the mon.txt. We use the ctc2dat command and provide the mon.txt. Now we have all these modules and all the information we need. We now use the ctc post because we have the mon.sym and mon.dat file. We want a profile report, so textual profile report, so we will look at like that. So we use more and go through the whole thing. Seems everything's alright so far. So we can also use ctc to HTML. As input we use our profile txt. Now we can browse it in our system. As you can see here, we use pragma before the output comes out. Maybe we could use a pragma skip in this case. You might ask why we use pragma ctc append. As you can see, we will never exit this program, so we have to tell ctc somewhere to output its measures. We can either use this pragma or we can use ctc.ini and, for example, embed this on the embed function name. So we could, for example, if we have a function called foo, every time foo gets called, ctc has an append, a ctc append, and outputs its contents. This could be used, for example, for a timer or a clock function that is always called when a specific time or a specific time interrupt occurs or something like that. So that's it. We now will do a short example with our prime example. In this case, we only will use the calc.c and a unit testing tool called µCunit. I will show you quickly how this whole process will be done, and then we should be able to just use a unit testing tool here. So how can we design and prepare us for our tests? First, we have to do some configuration. We have our source files here. We have one main part, that's our system under test. We will exclude the serial.c because we know this is working. We don't have to do code coverage on this, but we need to do code coverage on this calculation algorithm. That's the default example of Testwell CTC. We have provided here a small prime checker. We also have a test part of the source code. We have an implementation of our a system init, a system shutdown, system reset, system save state. The ones we really use will be system init to initialize our serial interface, and we will use this serial path string as well as a shutdown and a while loop to get this whole thing done. And we have an integer writer right here. Okay. So CTC has to know where or when to write out its results, because we only instrument one file, our calc.c, and not serial.c, not system.c, not main.c. We have only access to the calc functions, or could use our CTC pragmas in the calc function to not put gibberish into our source file. We just embed the function name that is used last. For this example, the calc.c with the embed function name option. One CTC append is put here, put here, put here, and put here, just everywhere where this function could exit. So now we have to set it all up and run it in our CTC. We will just rebuild the whole thing. As you can see, it steps through all of our things. We now upload it to our AVR. We now look at the result in our PuTTY. We log it again into our mon.txt. See, we have free passed, everything's all right. Close it. We open again our project folder. Let's log it again. Now, to convert, we will use CTC to DAT -I and our mon.txt. We will show it now. Everything's done. We close the session. We now have received 3 datas. We now do our report generation. I just put here a small tool to make this a bit easier. First we generate the texture report, and now we generate the HTML report and look into it. As you can see, we have one file here. We have the calc.c. So we run through this, but everything else we have failed so far. So this brings us to one of the last steps. Reiterate the design, reiterate the whole thing, and I will show you just quickly how to do that. Okay, we know we don't use this, so this could be a 25 because the next prime is a 5, and 3 would quickly be resolved, so we wouldn't get into this loop. But we would need a divisor, so we would use here 25, and we would use the value 3, and we would try to get, for example, a 17, just to have another prime. So let's just put it into our test case. So we need 3, 4, 17, 25. So we also have to adapt. This is a prime, this is a prime, this is a prime as well. This shall be a prime and this shall not be a prime. Okay, rebuild. Should build the whole thing. We put it via AVR-Dude up to our system. Restart again putty. Count 3. Logging. Close this whole thing. We generate first a texture report. Now we have more data than before. We generate the report. Now we see everything has been covered, and that's how you do it on an Arduino-like device. Thank you for your attention and have a nice day.